In this video, we're going to go over more examples on how to proceed to find the interval of convergence of a power series. And we're going to go through all of these 6 examples here, starting with a series from 1 to infinity of x minus 3 to the n divided by n squared. This is a power series centered at 3, so we should expect to find an interval centered at 3. And we look for the condition on x, in other words, in terms of the distance to 3, for this series to be absolutely convergent. It's going to be the case on the open interval of convergence. And then we'll have to test the endpoints of that interval. So the way to find this condition on x for the series to be absolutely convergent is typically using either the ratio test or the root test. And very often we could use one or the other. Most of the time we're going to use the ratio test. We're going to use the basic convention that a indexed by n denotes the general term of the series we're considering. So in this case, an is x minus 3 to the n divided by n squared. And so if we look at the ratio involved in the ratio test, it's the absolute value of the ratio of two consecutive terms, an plus 1 over an, which in this case is absolute value of x minus 3 to the n plus 1 divided by n plus 1 squared, that's an plus 1. Then we multiply by the reciprocal of an, which is n squared divided by absolute value of x minus 3 to the n. X minus 3 to the n plus 1 divided by x minus 3 to the n simplifies as just absolute value of x minus 3. And of course, n squared divided by n plus 1 squared can be written n over n plus 1 squared. What we're interested in, if we're using the ratio test, is the limit as n goes to infinity of this quantity. And you see that n over n plus 1 goes to 1, and therefore so does its square. So that the limit of this ratio as n goes to infinity is simply the absolute value of x minus 3. In other words, the distance between x and 3. According to the ratio test, we can conclude that our series is absolutely convergent if the distance from x to 3 is less than 1, and divergent if it is greater than 1. And so we have an interval of convergence that is an interval centered at 3 and of radius 1. In other words, it's going to extend from 2 to 4, and we have to test separately these endpoints 2 and 4. So we're going to take a look at what happens when x equals 2 and when x equals 4. So these are the two endpoints for our interval. And when x equals 2, so we replace x by 2 in the expression for the series, namely we get 2 minus 3 to the n over n squared, so that's negative 1 to the n over n squared. That's the general term of the series when x is 2. And this is an absolutely convergent series because the series of 1 over n squared is a convergent p-series. So the series is going to be convergent for x equals 2 and also for x equals 4 because we get the same convergent p-series at x equals 4. If you plug x equals 4, you get 4 minus 3, 1. 1 to the n is 1. So that means that the interval of convergence is the interval from 2 to 4 where we include both endpoints. For the second example, we're looking at the series from 0 to infinity of negative 1 to the n, x to the n divided by n plus 1. So this is a power series centered at 0, where the coefficient, the nth coefficient, is negative 1 to the n over n plus 1. As usual, we use the same convention for an. An is a general term of our series, and we look at the ratio of two consecutive terms in absolute value in order to try to use a ratio test. So in this case, we get, well, when we use the absolute value, the negative 1 to the n disappears, it's always 1. So we have absolute value of x to the n plus 1 divided by n plus 1 plus 1, so n plus 2. That's an plus 1. Then we multiply by the reciprocal of an, so that's n plus 1 at the top divided by absolute value of x to the n. Absolute value of x to the n plus 1 divided by x to the n cancels out to be just absolute value of x, and then the n plus 1 over n plus 2 is a factor in front, which as n goes to infinity goes to 1, so that the limit of our ratio is absolute value of x. And therefore, by the ratio test, we can conclude that our series is absolutely convergent whenever this limit is less than 1, so when absolute value of x is less than 1. and divergent whenever this limit is greater than 1. So we have here an interval of convergence that is going to be an interval centered at 0 of radius 1, so it extends from -1 to 1. We have to test these two endpoints, -1 and 1, separately. And specifically for x equal 1, if I plug x equal 1 in my series, x to the n becomes just 1, so we are left with a series from 0 to infinity of -1 to the n divided by n plus 1, which is clearly a convergent series by the alternating series test, because the sequence of absolute value of the terms, 1 over n plus 1, is decreasing with limit 0. On the other hand, if x is -1, then I get at the top -1 to the n multiplied by -1 to the n. That's -1 to the n squared, which is just 1. And so we get the sum from 0 to infinity of 1 over n plus 1, which of course, if you think about what it is, when n is 0 you get 1, when n is 1 you get 1/2, when n is 3 you get 1/3, and so on. So it's really just the same series as the series starting at 1 of 1 over n, which is a divergent p-series, and therefore we know that the series is divergent. So we have this interval from -1 to 1. We have seen that we need to include 1 and exclude -1, and therefore the interval of convergence is from -1 to 1, with -1 excluded and 1 included. In the third example, we look at the series from 0 to infinity of 3 to the n, x to the n divided by n plus 1 squared. It's again a power series centered at 0, so we expect the interval of convergence to be an interval centered at 0. We're going to use again the ratio test with the same convention that an is a general term. So the ratio involved in the ratio test, an plus 1 here is 3 to the n plus 1 multiplied by, if I'm in absolute value of x to the n plus 1 divided by n plus 1, that's n plus 2 squared. And then I multiply that by the reciprocal of absolute value of an, which is n plus 1 squared divided by 3 to the n absolute value of x to the n. Now you have 3 to the n plus 1 divided by 3 to the n. That will be just 3 at the top. And then you have absolute value of x to the n plus 1 divided by absolute value of x to the n. That's just absolute value of x to the top. And then you also have n plus 1 over n plus 2 squared. As n goes to infinity, n plus 1 over n plus 2 goes to 1, and so does its square. And therefore the limit of our ratio is 3 absolute value of x. According to the ratio test, we can conclude that the series is absolutely convergent if that limit, 3 absolute value of x, is less than 1, and divergent if that limit, 3 absolute value of x, is greater than 1. This condition, 3 absolute value of x less than 1, is really saying that the absolute value of x is less than 1/3. So in other words, the condition on x is that its distance to 0 be less than 1/3, and that's our radius. So we have an interval of convergence which is centered at 0 of radius 1/3, so it extends from -1/3 to 1/3. And we have to test these endpoints separately. Specifically, when x is 1/3, x to the n is going to be 1 over 3 to the n. So at the top we have 3 to the n multiplied by 1 over 3 to the n, and then this is divided by n plus 1 squared. That's our general term when x is 1/3. Of course, 3 to the n multiplied by 1 over 3 to the n is 1. So we end up with a series of 1 over n plus 1 squared. Shifting the index, it's really the sum starting at 1 of 1 over n squared, which is a convergent p-series, because p is 2, which is strictly greater than 1. And if we look at what happened at -1/3, if I plug x equal -1/3, we get -1/3 to the n. That's -1 to the n divided by 3 to the n. The 3 to the n cancels out, and we end up with a series from 0 to infinity of -1 to the n over n plus 1 squared, which is not only convergent but absolutely convergent, as we have seen when testing x equal 1/3. Therefore, the series is convergent at both endpoints, and the interval of convergence is the interval from -1/3 to 1/3, including both endpoints.